Have you ever looked at a microchip and just wondered, how do they even make this thing? How do you take lines of code, an abstract idea, and turn it into this incredibly complex, physical piece of hardware? Well, that's exactly what we're going to break down today. We're going on the journey from a digital blueprint to physical reality.
So let's start with a crazy question. How would you build an entire city? We're talking a billion buildings, all perfectly connected, on something as small as the tip of your finger. It sounds impossible, right? But this is literally the puzzle that chip designers have to solve every single day. And the entire field dedicated to solving it, it's called physical design. Physical design is really where the rubber meets the road. It's the engineering magic that takes an abstract circuit diagram, the what it does, and transforms it into a super detailed physical layout, the how and the where every single component goes. This becomes the master plan, the final blueprint for our tiny micro city. Okay, so just like any good architect, you don't just start digging. You need plans, you need rules, you need to know what you're building. And in chip design, it's no different. Everything kicks off with a few key digital inputs. Think of it like this. Every project starts with 3 essential documents. First step, you've got the net list. This is basically the city census. It's a complete list of every single building and a map of all the roads that connect them. Then you have the libraries. These are like your approved architectural catalogs, a collection of pre-designed, pre-approved structures you can use. And finally, you have the constraints. These are the city's zoning laws and performance goals. Things like traffic needs to move this fast and the whole city can only use this much power. All right, with those plans in hand, it is time to draft the high-level master plan for the whole chip. This first big stage is often called chip planning or floor planning. And let me tell you, the decisions made right here, right now, are absolutely crucial for everything that follows. And this whole planning phase happens in a few key steps. First, engineers partition the chip into major districts, and then they floor plan it, which is basically deciding where the huge skyscrapers, like the CPU cores or big memory blocks, are going to go. Next, they place the I/O pads, which are essentially the highways, the on-ramps and off-ramps connecting our city to the outside world. After that, a really critical step, power planning. You've got to lay out the entire electrical grid to make sure every building gets power. And finally, they mark out the residential zones. These are the huge open areas where millions and millions of smaller components are eventually going to live. So, we've got our districts, our skyscrapers are in place, our power grid is laid out. Now comes the part that is just truly mind-boggling. Placing every single one of those smaller buildings, what we call standard cells. And when I say millions, I'm not exaggerating. We're not talking about a few thousand parts here. We're talking millions, sometimes even billions of these tiny logic gates that have to be placed perfectly inside the zones we just mapped out. The scale is just staggering, which is why this whole process has to be almost completely automated. So what's the number one goal for the software doing all this placing? It's actually pretty simple: efficiency. The main objective is to minimize the total length of all the wires. Just think about it. If you place 2 buildings that talk to each other all the time, right next to each other, you shorten the commute, right? And in a chip, a shorter commute means less delay, less power consumption, and a faster city overall. And this is where you see a really cool contrast in the design. On one side, you have the macros, those big skyscrapers. There aren't that many of them, maybe tens or hundreds, and placing them is often a delicate, manual task that needs real human expertise. But on the other side, you have the standard cells, the millions of identical little houses. You can't place those by hand. It's a massive, complex puzzle that only a powerful piece of software can even attempt to solve. Okay, all the buildings are in place, from the biggest skyscraper to the smallest house. Now what? Well, now we have to build all the roads. This phase is called routing, and it always starts with the single most important network in the entire city: the clock. You can think of the clock as the city's heartbeat. It's this pulsing signal that synchronizes every single thing that happens, making sure all the different parts act in perfect unison. And because it is so critical, the clock network gets the VIP treatment. It is built first, using the best resources, the most direct paths, before any of the other traffic gets in the way. Now, the biggest enemy you're fighting when you build this clock network is something called clock skew. See, even at the speed of light, it takes time for that clock pulse to travel across the chip. Skew is that tiny difference in when the pulse arrives at one building versus another. If that difference is too big, we're talking just a few picoseconds, it can cause total chaos. So the whole point of what's called clock tree synthesis, or CTS, is to build a perfectly balanced, symmetrical network to get that skew as close to zero as humanly possible.
So once that perfect clock network is in place, it's time to connect everything else. And this happens in two main stages. First is global routing. This is like planning the interstate highway system. The software doesn't draw the exact lanes yet, it just figures out the general path that bundles of wires will take through different regions. Then, once that high-level plan is locked in, detailed routing takes over. This is the super nitty-gritty work, paving every single street, every alleyway, creating the exact physical wires on many different metal layers to connect every single component. So, in a perfect world, the whole process would be this beautiful, straight line. You zone the city, you place every house, you build the central clock tower, you pave all the roads, and bam, you have a perfect final blueprint.
Yeah, but as you can probably guess, reality is never that simple. The real design process is full of feedback loops. For instance, what happens if, during routing, the software finds a massive traffic jam, a spot where there are just too many wires trying to squeeze through a tiny area? That's called congestion. And when that happens, you can't just keep going. You actually have to go back a step, back to placement, and start moving the buildings around to clear up some space. This back and forth, this iteration, is a massive part of getting a design that actually works.
So after countless hours, and I mean countless hours of planning, placing, routing, and going back and fixing things, the design is finally done. It's been checked, double-checked, and verified. Now it's time to lock it down and send it off to be built.
This huge milestone has a special name, tape out, and it is a massive moment for the entire design team. It's a time for celebration because it marks the end of an incredibly difficult, long, and complex process. The blueprint is officially final. And what is that final blueprint? It's a specific type of file called a GDS file. This file is the grand finale. It is the culmination of all that work. It contains the exact geometric patterns for every single layer that will be used to manufacture the chip. Every transistor, every wire, every connection. It is the master set of instructions that the factory, the foundry, will use to actually build our microcity.
So there we have it. The digital blueprint is finally finished. But honestly, that's only half the story. The next monumental challenge is actually building this thing, turning those patterns in a file into real silicon. And then, once it's built, you have to test it to make sure every single one of those billion buildings is working just right. But that, well, that's a story for another time.